Hello, hi everyone. So welcome back to my channel and let's just start with today's Leetcode question, that is count square submatrices with all ones. Until now we have completed 15 challenges. In case you have missed any, you can watch it on my YouTube channel. I've created a playlist for the same. So let's just quickly read the problem statement. So we are given a m cross n matrix of ones and zeros and we have to return how many squares submatrices have all ones. So if you can directly see this example. So for this 2 cross 2, we have 1 0, and similarly in the 3 cross 3, we have 2 zeros. So we cannot make them. But if you see in this 2 cross 2, 1 1 1 1, so that will be 1. Similarly, in this 2 cross 2 matrix, we have already all ones. Similarly in this, and similarly in this, and in this 3 cross 3, we have all ones, so that will also be included, and all the ones are 1 cross 1, so that is also an answer. So total count will be 15. So yes, so as in the explanation mentioned, there are 10 squares of side 1. Okay, so these are 10, 4 3 3. Then 4 squares of side 2. Okay, so 2 cross 2 matrix are 4, and this one, then this one, and this one. Okay, and 1 square of side 3, so this is 1 1 1 till this, so this is 3 size. So total are 10 4 1 15, right? So now we will just move quickly to the intuition part. Okay, so we can quickly start the intuition part. So we have this example, right? So if we check how many are this square matrix with all ones, so these are 1 cross 1. So first what we'll do, this is 3 cross 4, right? Now minimum of this will be 3, so maximum size square submatrix will be 3 cross 3, right? It cannot have 4 cross 4. So now before this, 2 cross 2 can also be there and 1 cross 1 can also be there, right? So first we will calculate. So 1 cross 1 are all the ones, so it will be 10. 2 cross 2 are first. If you see, this is not because this is 0 including. So if we shift the window, this is also square matrix with all ones, so 2 cross 2 is 1. Similarly this is also, this is also, and this is also. So 4 are 2 cross 2. This cannot be a 2 cross 2 because it includes 0. Now 3 cross 3 is only 1, the big one, so this is 1. So total is 15, right? Now how we should start the intuition part, how we can discover how to approach this. So if you see directly, we have this, that 1 cross 1 you can directly find. Now you should start with 2 cross 2. How you can know that this will help, this is included in your 2 cross 2 matrix, that is all the ones. If you see directly that it is dependent on the adjacent, the diagonal, and the below one, right? If you know that this is your one which is included in the square matrix of 2 cross 2 size, then they all should be 1. And if they all should be 1, that means that you are included in your, plus you can also get your one more, so it will be like, sorry, so it will be 1 plus 1, that is 2, right? But you know that your 1 can also be a part of 3 cross 3. So, and 3 cross 3 is this. Now you have to check for all of these, right? So instead of going this way, what you can do, you can start from bottom, right? Now what you will do, you start from bottom. This is 1 cross 1, right? It cannot be checked for this, so it cannot make your answer, but it is make your answer for 1 cross 1. So now it is already 1, so it will make your answer. Same here, it cannot check for this, it can only check for below, so 1 only. So this whole row and this whole column will be same. But when you start from here, you can check for, this is 1, this is 1, and this is 1, right? So it can make 1 itself, 1 cross 1, and 2 cross 2 also. So how many it can make? It can help you make 2, right? So this one will be making 2 matrix, 1 cross 1 and 1 2 cross 2, right? Similarly, now we'll just erase it. So now if you check for this, it can make this one, it can it can make itself. And now for 2 cross 2, because it cannot make 3 cross 3, it will go here. So for 2 cross 2, how it will check? If this is 1, yes, it is already 1 and greater than 1, and it is 1 and it is 1, right? You can check in the matrix. Yes, it is 1, it is 1, it is 1. So how much it will make? It can make 2. It cannot make 3, so it can make 2. Now for this, how you can check? If you can make itself, yes. If this is 1, this is 1, this is not 1, so how it can make? How many it can make? It can make only 1, so we already have 1. Now this is already part done, so now we'll start from here. For this one, it is 1, it is 1, it is 1. How much it can make? 1 itself and 1 more, so 2 will be here. Now this one, it can make 1 itself and 1 here, 1 here, 1 here, so 2 it can make, right? So 2 it can make. Now this one makes 1 itself and 2, so we already have 1 count. This one already can make itself 1 and 1 more of this size, so already 2. And this one can only make 1, so already have 1. Similarly, all the values, if you count with the sum, so you can have your answer, right? How it can be 2 plus 2 plus 2 plus this is 8, 9, 10, 11, 12, 13, 14. Sorry, we missed one. So okay, so if you check, we have done something wrong here. So for this position, right, how we will calculate? Because this one can help me make one with these, right? And this is already making, if you see, this is already making one including itself and one with the other one, like below 2 cross 2. And you know that this is also making 2 cross 2 and this is also making 2 cross 2, but you know that all the below are 2. Okay, below at least you have 2 ones, and here you know that at least 2 ones are here, and with this you know that there are at least 4 ones here. So how much you can make? One is 2 cross 2 here and one is 3 cross 3, right? One is 3 cross 3 and one is 2 cross 2. How you know that this position, if you see, it is making 1 itself plus 1 it is making with the like additional itself, next one. So you know that at least 2 ones are there, and from here you can check at least 2 ones are here, and with this position you know that at least all the ones after that are here. So you can make one 3 cross 3 also, so your value will be 3, because one you can make itself, one is 2 cross 2 and one is 3 cross 3. Now how you are making it 3? If you check, you are just checking their additional values, this position, this position and this position, and if you're currently 1, then you are just updating your value with one addition. So the logic is current position of ij, what it is holding, it is checking for I plus 1. So next row it is this, and same column, right? So this position and this position will be I same j plus 1, and the diagonal position is I plus 1 j plus 1. So what it is checking? It is checking with which of them it can make, and if you are currently, then you will add 1 to it, right? So it will be minimum, because if you see here, this is 2, this is 1, this is 1. It can make the next values, it can make 1 square with itself and 1 square with the next values, but it cannot make, because then it will have to be 3 cross 3 and it is of no size. So minimum of these values, right, minimum of these 3 plus if you are currently 1, so right, if you are 0, then you don't have to do this thing, this logic. That means that you cannot make your answer, right? So these 3. Now how you should go? Since we have to, like, for each position you have to check for next one. So you will start from 0th position, right? Now one more try run. So what you will do, you will do here only. So 1 0 1 1 1 1 1 1 1, right? Now first you will come here, right? You found one. So what you will do, you will go for this and this, and these position will go for their next step. So this. Similarly, if this is 1, this is 0, so it will not go. Okay, we'll remove it. But this is 1, this is 1, so it will check for this, will check for this will check for these three. Similarly, when you go here, it will do its part, it will do its part, it will do, and it will do, because these are the, like, borders. So they will not affect, they will not check for their next one. But if you see that for this you are going for this one and this one, and when you come to this one, it will also go for this, it will go for this, and it will go for this. Now when you come to here, since it is also one, so you have already visited this place from this position. Now for this you are again visiting this, right? So if you see from 0 0, if I make the chart, small chart, so from 0 0, where three places you are going, this is same row, next column, next row, same column, and next row, next column, three positions, this one and this one. Now for 0 1, which two positions you are going? Three positions, sorry. So for 0 1, which three positions you are going? That is second row, 0th column, and this is 1 cross 1, this position, and this is 2 cross 1, right? Okay, so one mistake, sorry. So for this will be 1 cross 0, and we will replace it by 0 cross 1, right? So which three positions now you will go for this? 0 for 0 1, 1 will be I plus 1 j, so that will be 1 cross 1, right? And one more will be ij plus 1, so 0 with 2, and 1 plus 1, so it will be 1 cross 2, right? Now something you are seeing, what, that 1 cross 1 is already being visited first time, then it is already being visited here, then it is also being visited here. So it is being visited three times. If you see from here, first it will visit from 0 0. Now when you go for here, you will be visiting here, and from here also you will be visiting here, right? So if you try making this recursion tree, so this is recursion tree, because you are going for every position, you are going for three positions, and for every three of them you are again going to three. So this is a recursion tree if you try to make, and you are seeing that there are some places that you are being visited again and again, and that will cause time complexity issue, because if one position is being visited multiple times, that will increase your time, right? Increase your time. So now what you can do, when you have visited this place, okay, you can hold your answer in some variable or in some place, and when you visit this place, you already know that this position 1 cross 1 already have your answer as somewhere like 2 or 1 or 0, anything. So then you can directly have your answer as 0 written, instead of going from 1 1 to three places again, right? So what we'll do, we will create a matrix. We have this 1 0 1 1 1 1 1 1 1, right? Now if we go for this one, we will go to here, here, here. Since it is 0, so we will not go anywhere. It is 1, so where will we go? Here, here, and here. When you come here, you will stop. So now you will directly update your here a position. Now when you come to here, since you cannot move anywhere, so you will update your position here. Similarly, when you come to here, you will directly update your position here. When you come back, okay, now you know that this is already our answer 1, this is 1, and this is 1. For this, how much you have your answer? So it will be 2, because 1 you can make your itself. Okay, I will not update you guys, sorry. So how much you can have your answer? So 2, because 1 is already here and these are all ones, so your answer will be 2, because you can see that 1 you have already made and 1 you can make with itself, so you will place your answer here. Now when you try computing for this, okay, and now this will compute for this and this, right? This is already the same, so you will just place it 1, okay, because this is a end, you cannot have your answer. Now you go to this position, you already have 1, so you will directly return it. Now it will check for this position, so this position is already giving you 2, you don't have to compute for again. So now you get your answer as 2 1 1, and if you know that this one will already make 1 your answer, and with these all positions as 1 it can make you 1 more, so the minimum of them will be 1, and you already have 1, so you will make it as 2. Now when, because this is 2, so you can this is 0, you cannot go anywhere. For this 0, what you will do? For this 1, sorry, so you will directly replace it. Now for this one, you have to go for each position and get the minimum. So this position is 0, this position is 2, this position is 2, right? So minimum of them will be 1, sorry, 0, and you have 1, right? So how much is your answer? 1, right? So now if you try to compute total of this, your DP array, this is your DP array. So 1 1 is 2 to 4 6 8 10. So 10 is your answer. You just have to add all the values, right? So what I was telling, that instead of computing again for the same position, you can have your one storage that is of same size as your matrix, and first whenever you encounter any position ij, you just replace in the DP array that value, and before that you can directly check if you have computed that place or not earlier, and if you have, that means that you don't have to compute it again and go in your recursion tree, so that it can save you time, right? So this is called recursion memoization. So memoization is basically means that you are having some memory before computing. So memoization, this thing. So at the time complexity in this case will be big of n cross m, because you are going for each of the value one time, suppressing the calls, right? So you are going n cross m, or this is m cross n, when whatever, and the space complexity you directly see, we are using n cross m size matrix. So this is called recursion with memoization. This is a recursion with memoization, and this is one type of DP approach, and other type will be tabulation. Now the difference between this recursion with memoization and tabulation is, if you see that you are starting from the this position and going till this to get your answer, and when you reach the bottom, this is a bottom, let's just say last position, and from this position you are building your answer to the top. So this is called top down, okay, because you are going from the top, this, let's just say top thing, and going down to make your answer. But what is the tabulation, right? So tabulation just the modified form of this memoization. In the tabulation you also have one DP, this matrix, but in that what you do, You don't have to do this recursion thing and call your function. You can directly go over this matrix, and you know that this position or this position and this position, for all of them you already have your answer as the one in the matrix that you already have. So in the DP array you will directly populate it 1 1 1 and this one and this one. Now from this position you will go upwards. Okay, up. From this position you will go up and make your answer. So first you here, then here, then here, then here, and you will make your answer. And now you get your answer when you add all of them. So for this, if you know that your our logic was minimum of all the positions I plus 1, and this is next row, this is next column, and this is diagonal. So it will check for all of them. Minimum is 1 and your current value is 1 is, so it will give you 2. Similar for this, what is minimum of all of them is 1 and your current is 1, so 2. And for this it is 0, so you will not do it, you will directly place it. Now this is 1, so minimum all of them is 0 and you currently have 1, so you will update it by 1 sum. So now you know your answer, that was 10, and it will give you the same, because if you see the matrix is same we have made. So tabulation is similar form of this approach, but instead of going in the recursion you just go over the array, and this is called bottom up, right? Bottom up approach. Why it is bottom up? Because you are going from here, this is, let's just say, bottom, and you are going above, and in the above approach that this is the top and you are going till bottom here, right? From bottom, and this is the arrow that you can see directly. This is how you are making your answer. So this is top down, and here you are making your answer as way up, so bottom up. That's why they are called. So you don't have to get confused in this bottom up top down. You just build your intuition first, the logic that you can do, and then how you can optimize the calls, and that will give your answer. You don't have to everything memorize that this is top down, you have to do bottom up tabulation, anything. And this is your space and time complexity, and this will be similar in the tabulation. So now we will move to the coding part to do that and make it better understand. Okay, so we can start the coding part. So I've created these two variables for storing the size. Now what we'll do, we will create one dp array, vector of vector dp, and dp size will be similar, so m cross n. Okay, so m and n, right? And currently we will do place all of them as -1, right? Now we will go for, first we can have our answer variable, and we will go for each position in this matrix and we will build our answer. So for in 0 less than n, okay, less than m plus plus, and for int j 0 till n j plus plus, right? And now we will go, we'll create a function solve that will be taking ij and matrix and our dp array, right? So void solve int I int j and r this matrix, okay, and our dp array. Okay, now if we are solving this, we are making the dp array. Now what we'll do, we can directly add the answer to the dp. Okay, this will get your result, so we can directly add it in our answer. So answer this, right? And then we can return our answer. So we will make it, okay, so we have to make it in type. Now what you have to do, we will check if I reaches beyond this. Okay, if I reaches beyond this, then we don't have to like do anything, we'll just return 0. So if I is greater than equals to, what is this, matrix dot size, okay, or if our column, so I is reaching this end and column is here, so j will be greater than equals to matrix 0 dot size, so this will return 0. Now if you know that this is 0, you don't have to compute, so you will again check if matrix of I j is 0, you can directly return 0. If it is not 0, then we have to compute for the right, left, okay, right, diagonal and bottom. So in right will be, we'll get our value, solve, right will be I same, one more column, and matrix will be similar and dp will be similar. Then bottom I plus 1 j same, matrix and dp. Now diagonal, so diagonal will be solve I plus 1 j plus 1 matrix dp. Okay, now what do we have to do? You know that currently you are R1 and you have your answer from all of them. Now you have to just return minimum of your right and minimum of diagonal and bottom plus 1. Okay, so this is the recursion thing that we have to do. Now we have to use this dp. If you know that this position ij is already computed, so dp of ij is not equals to -1 because we have placed -1, that means it is already visited, so we'll return dp of ij directly. So it will be if it is already computed. Now if it is not, then we will go for all positions, and when we are returning we will just add this value to our dp of ij so that it can be reserved and called here for the next calls. So I think this will solve our answer, and let's just try to run it. Okay, it is running fine, so let's just try to submit it. Yes, it is running perfectly fine. So thanks everyone for watching. In case you do like this video, please do hit that subscribe button and turn on the notifications. And in case you have any queries or questions or anything you want to say, you can comment on the video. I will surely review it and work upon it. And yeah, so this is the approach for the recursion. You can directly do the tabulation part instead of going for these. You can directly start from the bottom position and make your answer. If you want, you can comment. I will give the code in the GitHub repo.